Okay, so we're now going to look at the final part of hypothesis testing, which is looking at what are called two-tailed tests. So for a two-tailed test, what we know is that what we're testing for is whether there is a difference or a change. So we don't know which direction it is, we don't know if it's an improvement, we don't know if it's a decline, so we don't know if it's more than or less than. We just know that we think that there might be a change, it might be different. So what's important here is if we're testing a significance level, so let's say 5%, that means we're looking at 25% at each end, okay? So sometimes the information will still imply that we're looking at one end in particular in terms of the sample size, but the percentage we're comparing to is different. So on the third to last slide, so the one titled two-tailed test, we're going to go straight into the examples. So over a long period of time, it has been found that in Rico's restaurant, the ratio of non-vegetarian to vegetarian meals is 2-1. In Manuel's restaurant, in a random sample of 10 people ordering meals, 1 ordered a vegetarian meal. Using a 5% level of significance, test whether or not the proportion of people eating vegetarian meals in Manuel's is different to that in Enrico's. So the fact that they've used the word different implies that it is a two-tailed test. So we need to set up our our hypotheses in the same way we would last time. So X is binomially distributed, and we're looking at a sample size of 10 people, and the probability of a vegetarian meal at Enrico's is 1/3, because it's in the ratio 2-1, that means 1 out of 3 people choose a vegetarian meal. Our null hypothesis is that the probability is 1/3. Our alternate hypothesis is simply that the probability is not equal to 1/3. So we don't know if it's one way or the other, we just know that it's not equal to 1/3. So what happens in Manuel's restaurant is that 1 person out of the 10 chose a vegetarian. So we need to see what is the probability that X is less than or equal to 1, because we're seeing 1 as being very, very small, so it's 1 or less. What's the probability of 1 or less people choosing a vegetarian meal at Enrico's restaurant, given this probability here, which is 1/3. So on our calculator, so go to the distribution, we're going to go to normal CD, variable, so it's 1 or less, with a sample size of 10 and a probability of 1/3. So the probability of 1 person or less choosing a vegetarian meal in a sample size of 10, with a probability of 1/3 of people generally choosing a vegetarian meal, is 0.104. Now we are testing this at the 5% level of significance. Now that means we're looking at 2.5% at the bottom end and 2.5% at the top end. So we've got to compare this to 2.5%. Now 0.104 is larger than 2.5%. So therefore we accept the null hypothesis, the proportion in each restaurant is not different. Because with 1/3 of people generally choosing a vegetarian meal, in a sample size of 10, actually it's fairly likely that only 1 person might choose it. given that we think a third of people normally do. So that probability is larger than the 2.5% that we are looking at, so therefore we accept the null. The proportion in each restaurant is not different. Okay, so on to example number 2. So these are questions from the exercise, both these next questions, because I don't think one question is enough to practice hypothesis testing. So I've chosen different styles, and both of these are going to look at critical regions, but they're going to look at critical regions in slightly different ways. So question 7, explain what is meant by a hypothesis test, a critical value, or an acceptance region. So a hypothesis test is looking at a test where you're testing a hypothesis against a significance value. The critical value is the value at which you would reject the null hypothesis and accept the alternate hypothesis. And the acceptance region is not really language that they look at very often. They normally just call things a critical region, and it's things that fall within this region that would allow you to accept the alternate hypothesis. So Johan believes the probability of him being late to school is 0.2. To test this claim, he counts the number of times he is late in a random sample of 20 days. So he's either late or not late. So x being the likelihood of him being late is binomially distributed. He's testing it over a sample of 20 days, and he thinks he's late 0.2 of the time, so 20% of the time. Find the critical region for a two-tailed test at the 10% level of significance of whether the probability he is late for school differs from 0.2. So if you imagine this is our probability scale, because we're looking at the 10%, that means you've got a region at the bottom and a region at the top of both of 5%. Although this one at the top, because we're looking at obviously less than values, means we're going to compare it to a 95% value on our calculator. So if this is spanning 20 days, there'll be a number of days here that's so small that actually the probability of him being late must be less than that. Or there's a range up here where he's late a large number of days, so the probability of him being late is bigger than 0.2. So they are our critical regions. So we need to set our hypothesis up first. Our null hypothesis is that the probability is equal to 0.2. Our alternate hypothesis is that it's not equal to 0.2. The question says differs. It doesn't tell you a direction, so it's just a change. That means it's a two-tailed test. Now the question tells you to find the critical region of a two-tailed test. It won't always do that. It will imply that it's a two-tailed test by using the word differ, so you need to be careful. So this is a bit like last time, where we're going to use our list function, our calculator, to find these values. So I need the probability, or the value, where the probability that he's less than or equal to a value is less than 5%. And I also need the probability that x is greater than or equal to a value is less than 5%, which would mean the probability that x is less than or equal to a value is bigger than 95%. So I know I've used lots of different letters, but you'll see what I mean as I'm doing it. So I'm going to do this bit first. So on my calculator, I'm going to go to distribution, go down, binomial CD, and I'm going to do the list. So I'm doing up to 20, but I'm looking at this bottom end. it's not likely that I'm going to have a lot of values. If it's 20% of the time, I reckon the cutoff that's less than 5% is actually going to be really small. So I'm going to do 0, 1, 2, 3, 4. I'm going to go up to 5 because 5 is 20% of 20. 4 is 20% of 20, so 5 is just over that. So the probability of that being the case is going to be quite high. So I don't want to go any further than that. Even though I could go up to 20, I'm not going to worry about it. Could go all the way up so that I can do this in one go. But you don't have to, okay? So I'm just going to go up to here for now. So my sample size is 20 and my probability is 0.2. So I need the first value where this goes over 0.05 so that I can find my cutoff. So I've got here 0 days or less, which obviously is just 0, is 0.0115. And then I've got 1 day or less, which is 0.0692. So this is outside of our range. We want it to be less than 5%, okay? So it's this one I'm talking about. So therefore, 0 days is our lower critical region. I'm now going to look at this part. So I now need to look at a value that crosses over into the 5% at the top end, which means it has the chance of getting less than or equal to a number must be bigger than 0.95. So I'm going to just do this whole thing again. And I'm going to look at the top end. So I'm going to start from about 10. And I'm going to go all the way up to 20. So it's a sample size of 20, probability of 0.2. Now, as you can see, actually, my numbers are already bigger than 0.95 because it's 0.99. They're already massively bigger, so I actually need to go back. It means that the region is quite large that's going to impact my probability. So what I can't do is insert it. So I'm just going to override. So I'm going to go from, let's say 6, 7, 8, 9, 10. And what it means is that I don't need any other values because I already know that 10 is bigger than 0.95, but I need the first value that's bigger than 0.95. So 0.913 and 0.967, so they're the ones either side. Like I said in the previous video, we do really need to put the ones at either side of our cutoff so that we're making it really clear to the examiner that we haven't missed a value. So 6 days or less is 0.913. And then the probability of him being late on 7 or less days is 0.968. So the probability that x is less than or equal to 7 is 0.968. So that means on the 7th day, the probability overlaps. So therefore, 8 days or more are going to be part of our critical region. So our critical region is either he's late no days or he's late 8 days or more, because the 7 is the first one that goes into that critical region. On the 7th day, he's on that overlap. So the next one that satisfies it is 8 days or more, because 7 is the first one in that boundary. This is probably the hardest concept to understand, because on the 7th day, the probability starts less than 95%. So on the 7th day is when it crosses, so therefore it's 8, 9, 10, 11 or 12 days up to 20 is our cut-off point. So it says state the actual significance level of the test. Well, the actual significance level is our probability of 0 days and plus our probability of 8 days or more. So the probability that x is 0 is 0.0115, and the probability that x is 8 or more is 1 minus the probability that it's 7 or more, which is 0.032. So therefore the significance is the sum of those added together and turned into a percentage. So 0.0435, which is 4.35%. So that is the actual significance. It says Johan discovers he is late for school in 7 out of the 20 days. Comment on whether Johan should accept or reject his claim. Well, 7 is between our critical regions. So it's not inside either critical region. So therefore we're going to accept the null hypothesis. So accept his claim that he is late to school 0.2 of the time, or 20% of the time. So I think it's these top-end critical regions that are one of the hardest things to understand, but you've got to imagine that 7th day is on either side. So part of that 7th day probability is outside of the region. So it's the first value that is completely inside, which is 8 or more, okay? So I think that's probably the most difficult concept overall that we're looking at. So I've got one more example to do, which is question 7 from the mixed exercise. Actually, I can't quite remember whether the question 7 I've just done is from the main exercise or from the mixed. Either way, they're question 7 from either 7D or from the mixed exercise. I can't remember which way round it is, so I apologise for that. But it's both the question 7, so don't do question 7 of either. So the national proportion of people experiencing complications after having a particular operation in hospital is 20%. A hospital decides to take a sample of size 20 from their records. Find critical regions at the 5% level of significance to test whether or not their proportion of complications differs from the national proportion. The probability in each tail should be as close to 2.5% as possible. So, 2 things that we need to think about in this question. Differs implies that it's 2-tail. Excuse me. And the question says the significance should be as close to 2.5% as possible. That does mean sometimes it will be larger than 2.5% or not quite within the range at either end. So that's why I've chosen this particular question, so that we can really think about the language. So the national proportion of people experiencing complications is 20%, and we've taken a sample size of 20. Obviously we know 20% is 0.2. So we want to find the critical region. So we're imagining our bar. Now we're testing at the 5% significance level. So we've got a region down here of 2.5% and a region up here of 2.5%. because my calculator obviously looks at less than, we're looking at a probability of 97.5%. So I need probability that x is less than or equal to a to be as close as possible to 0.25. So that's the first thing that we're going to look at. It's something that's as close as possible to 0.025. So this time when I go and do my distribution, I'm just going to put in my numbers 0 to 20 so that I can deal with both ends without having to type anything extra onto my calculator. So distribution, binomial CD, list, and I'm going to put in every single value between 0 and 20. Because it doesn't take me very long to do. So my sample size is 20 and my probability is 0.2. So what I'm going to do is I'm going to find the values at this end, the probabilities that are either side of 0.025, and then make a judgment about which one is closest. So I've got 0 days, 0.0115, and I've got 1 day, which is 0.692, both 3 significant figures. So that should be 0.0692. So I need to decide which one is closer to 0.025. So 0.025 subtract 0.0115 is 0.0135. 0.0692 minus 0.025. Obviously I know which way to subtract because I know which number is actually bigger. 0.0442. So therefore the closest is 0 days. So our probability at this end is 0 days. So I'm now going to go back to my distribution table. Unfortunately this one doesn't hold the list, it was just that I was trying to work these out. So maybe in the exam I might write down the ones in my region first so I don't need to actually retype them all in, but it's done now. 20 and 0.2. So I want the first one that goes just before 97.5% and just inside. So 97.5. Okay. So 7 days or less has a probability of 0.968 to 3 significant figures. And then 8 days or less has a probability of 0.990 to 3 significant figures. So they're the ones either side, either 7 or less or 8 or less. So I want the one that is closest to 97.5%. So 0.975 subtract 0.968. So actually by subtracting these, I can actually find out what's closest to 2.5%. 0.975 subtract 0.968, which is 0.007, and then 0.990 subtract 0.975. Is 0.015. So this one is closer. So the probability that x is less than or equal to 7 is the closest, so therefore the critical region is 8 days or more. If we found that this was closer, where the probability of 8 is less than or equal, sorry, x is less than or equal to 8 was closest, then 9 days or more would be our critical region. Now, it happens to be that both of these are, this one is within our region. This 7 was technically outside of our region, but it was the closest to 2.5% off the top end. So that's why we're looking at this one. State the actual significance of the test. Well, that's 0.0115 plus 1 minus 0.968. Which is 0.0435%. The hospital finds that 8 of their 20 patients experienced complications. Comment on this finding in light of your critical region. 8 is the cutoff, it's the beginning of our critical region. So 8 is within our critical region. So therefore we're going to reject the null hypothesis and accept the alternate. Oh, I realised I didn't set up my hypotheses. That is awful. Right, let's go back. H0 was the probability that it was equal to 0.2. And H1 was the probability that it's not equal to 0.2. I was so into the actual solving of the question that I forgot to write down my hypotheses. I would have lost marks in the first question, so I apologise for that. So we reject the null hypothesis and accept the alternate, which is that, is there a name for this hospital? No, it's just a hospital. So the hospital suffers a different proportion of complications to the national average. So there you go. These are, I think, probably the hardest part of stats. It's certainly the part that students find the most difficult. But this bar, like we've done it here at the top, any bar modelling can really help you picture where it is we're looking at. It's just the complicatedness at this end that we have to get our head around. But most of the question comes from setting up the hypotheses, finding the probabilities, and then finding a conclusion. So I'd like you to have a look at the exercise in the book 7D, but I'm also going to give you some exam questions on binomial distribution, probability distributions, and a little bit on hypothesis testing for you to do.